Hello everybody, welcome to part B of chapter 4.7. What we're going to be going over today is using completing the square as a strategy to rewrite integrals. And I also want you guys at the end of this lesson to be able to understand that sometimes a variety of strategies can be used to evaluate, and that there are some integrals we still don't know yet how to integrate. Okay. So let's jump right into an example of completing the square. Completing the square. Okay. Okay, so for completing the square, let's review what that even means. So basically, it just means that if you have a quadratic, like an x squared, a bx, and a c, what you can do is between right here where this plus sign is, we can add two things. We can add something and subtract something, and here's what I mean by that. We can do x squared plus bx, and then right here is where we can add parentheses a b over 2 squared, and we can subtract a b over 2 squared, and then we can add a plus c. So just right here is where we made something interesting happen. Right where that plus sign was before, we kind of threw this piece in there, which is allowed because if we simplified this, that minus that would be 0, so we're not doing anything that isn't allowed in algebra. What this allows us to do, though, is rewrite the quadratic in this following way. It would be x squared plus bx plus now this b over 2 squared piece, which is kind of cool. And then we say minus the b over 2 squared plus c. And this usually ends up being a single factor. It'll be a perfect square trinomial at that point. So what that would end up factoring out to be would just be an x squared, an x plus a b over 2 squared, right? If we have a perfect square trinomial, this is what we can do with it. And then we'd still have whatever that ends up being, b over 2 squared plus c, just some constant at the end. Let's do an example of where this would apply. So say we were asked to find the integral dx over x squared minus 4x plus 7. Okay. And then what we need to do there is complete the square. That's the step we're taking. For that denominator, right? This denominator we're going to complete the square with. So we're going to take that x squared minus 4x plus 7, and I'm going to rewrite it exactly as I did up here. I'm going to start with my x squared, my minus 4x. And now is where I'm going to add, I'm going to do plus b over 2 squared. So I'm going to do plus negative 4 over 2 squared and then I'm going to say minus negative 4 over 2 squared plus 7. And again, just to kind of reiterate visually what's happening here, this is what completing the square is. I'm just putting in that b over 2 squared plus and minus right here. Great. And now what happens is when I simplify this, I get x squared minus 4x plus negative 4 over 2 is negative 2. Negative 2 times 2 is positive 4. And then, again, I know this is going to be positive 4, so negative 4 plus 7 is going to be a positive 3. This, again, is a perfect square trinomial, which can be factored as an x, and then I use this sign right here, minus the square root of the last thing, a 2 squared, and then I have plus 3. So what I can do now is substitute in this equivalent expression to the denominator of my integral. Dx over x minus 2 squared plus 3. And what I can see now is that this is really close to the arctangent identity, but, or I guess I shouldn't say identity, integral is what I'm trying to say, where what we can say is that A is radical 3, right, because I'd have to take the square root of this thing, and that U would just be the whole binomial x minus 2. And when I use that information, I can rewrite my integral as 1 over A, 1 over radical 3, arctangent, U over A, so x minus 2 over radical 3 plus C. And now I'm done. Let's try another one. This one's phrased a little bit differently, but we're still kind of doing the same process. So it asks us to find the area of the region bounded by the graph of f of x equals 1 over radical 3x minus x squared, comma, bounded by the graph of, okay, that function, and then the x-axis, and the lines x equals 1/2 and x equals 9 over 4. Okay. Once again, it would be a good strategy here to complete the square so we can clearly have some things that are actually going to look like an easier thing to identify for our inverse trig integrals. Here's what I mean. Let's take, again, I want to write the step out that we're doing here, which is complete the square. And when I do 3x minus x squared, it'll be helpful to rewrite that as negative x squared plus 3x. Furthermore, what I can take out of that is a negative x squared minus 3x. Okay. And now we're going to complete the square with this piece here, with our negative x squared minus 3x. So here's what we could set that up as. We could have a negative on the outside of, I guess I should use brackets now, x squared minus 3x, and now is when my b value is going to come in handy. So I'm going to have plus negative 3 over 2 squared minus negative 3 over 2 squared. And then I can kind of have like a plus 0 here if you want to visualize what the constant would be. Plus 0. Though you can see why that's redundant. I am going to get rid of that. But that's what this whole thing is, as the quadratic. And now I can rewrite this half as that perfect square trinomial. So I can have a negative, and I can take the square root of the first thing, x. I use this sign here, minus, and the square root of this. And the square root of this really is just 3/2. So I would say 3 over 2. And then I would call that whole factor squared. That's how it works. A perfect square trinomial is factored in this way. And then what I say is plus a 3 over 2 squared. I want you to know that the sign there didn't really matter much, because what's going to happen is I did have this negative here on the outside of everything. So even though I did have a negative, like this would square itself away, and the negative right here would become positive, I still had a negative right here. But that negative was taken care of when I distributed this sign over. When I distributed the negative over, it became a positive, whatever that value was going to be, 3/2 squared. It should be like 9 over 4. Anyway, This is good enough for us for now. We've completed the square, and we can substitute this into the denominator under the radical of our function. So, under the radical of our function now, we're going to have our 3 halves squared minus x minus 3 halves squared, right? Just what we completed the square with. But remember, we're finding the area, so we're actually taking the integral, and our bounds are from 1/2 to 9/4. So we say 1/2 to 9/4, because those are the lines on the x-axis that we are bounded by. And we can just say area equals for this. Okay. And now I want you to see that we're actually pretty close to arc sine. What we have going on here is, so when I do the antiderivative here, it is just going to be the arc sine u over a. So it's going to be equals arc sine u. In this case, let's identify that first. U is x minus 3/2, and our a is just going to be the 3/2. So if I do arc sine u over a, I get x minus 3 halves over 3 halves. But again, this isn't an indefinite integral this time. This is a definite integral, so I'm going to have to use the fundamental theorem of calculus, and I'm going to have to evaluate it. There was a typo in here that I want you guys to fix. It was actually supposed to be from the lines x equals 3 halves. Sorry, I couldn't read my own handwriting there. So down here when we write our bounds, it should be from 3 halves, and then right here it should be 3 halves as well. So make that change, and then we still have 9/4 on top. Okay. And now what we do is, just like we always handle the fundamental theorem of calculus, we're going to take our bounds and we're going to substitute them into our function for x. So we're going to take 9/4 arc sine. I'm going to say 9/4 minus, and right now I'm going to do something. I'm going to change that 3 halves to a fraction over 4 so this gets a little bit easier. I'm going to call that 6/4. And then I'm going to say still over 3 halves minus this evaluated at the 3 halves. So arc sine of 3 halves minus 3 halves all over 3 halves. And when I start to simplify here, I can do 9 minus 6, which would be 3/4. And then remember, I'm dividing by 3 halves, so I'm doing 3/4 actually times 2/3. So 3/4 times 2/3 is going to be 6/12, and when I do 6/12, it's really just 1/2. And then when I do 3 halves minus 3 halves, I get 0, and then I'm just taking arc sine of 0, because if I have a 0 on top, it makes the entire thing 0. And when I do those trig evaluations and I subtract, I end up getting pi over 6 as my solution. Okay. I have just one more little quick set of examples to go through for you, and then I'll leave you alone. What I want to call this topic is comparing integration problems. Okay. So let's say we had a radical and we had dx over x radical x squared minus 1. This is what we've been doing for the last day. This lends itself pretty easily to that arcsecant integral rule that we know. So we know that this would become arcsecant absolute value x plus c.
you.
And so that's how we would handle that integration problem. But if we had one that looked really similar but was a little bit different, we'd handle it a completely different way. So if we had integral dx over radical x squared, oh, pardon me, that shouldn't be a d, it should just be x, excuse me, x over radical x squared minus 1, our strategy should be u substitution. That's how we'll take care of it. And we can call u x squared minus 1. We can call du then a 2x, which tells us we'd have to put a 2 into our integral. And if we did that, we'd have to put a 1/2 on the outside. So we'd have 1/2 du over u to the 1/2, which is the same as saying 1/2 integral u to the negative 1/2 du. Furthermore, when we use the power rule of integration, we would be saying 1/2 on the outside of u to the positive 1/2 over 1/2, or u to the 1/2 over 2 plus c. And when I multiply on the bottom here, I would get over 4 Hold up. I did that in my head, which is my issue. This should just be u to the 1/2 over 1/2. And then what we can do there is we can cross off the 1/2s, right? If I have like a 1/2 over here and a 1/2 on the bottom, then those get to cross off to become 1. And I end up getting u to the 1/2 plus c. But when I substitute u back in, I get x squared minus 1 to the 1/2 plus c. And that would be my antiderivative. Lastly, I want to show you, if we had an integral dx over radical x squared minus 1. Take a second and just think about that. Do we have a rule that takes care of that? And the answer is no. No, we do not have any rules that would take care of that for us. If we use like u substitution, we wouldn't be able to create like a dx or anything else back in there. If we try to do any other way, we really couldn't, because we have like this whole piece. If we had just radical x squared or just like radical x or something, we could, but because we have radical, this whole binomial, that's something we can't take care of. So we can just say, nope, can't be done. It can technically be done, but not until much later chapters in calculus. So that's it for today's video, and I will see you guys in class tomorrow.